So we stopped here last class where we derived the energy equation across the discontinuity representing the reaction zone, and we wanted to see how this looks like in what is now beginning to shape up as what's called as a Hugoniot plot. So this is what you would actually call okay, to some extent a simplified Rankine-Hugoniot equation. So how do you look at this this curve in the Hugoniot plot? The Hugoniot plot is a domain of P infinity with 1 over rho infinity, and then you begin to look at how this looks like. You now have a coefficient gamma over gamma minus 1 times P infinity divided by rho infinity. So this is itself like a product of P infinity and 1 over rho infinity, right? And of course we now say P naught over rho naught is like a parameter that represents like the initial state, and again you can look at a P infinity times 1 over rho infinity coming up over here with a different coefficient, of course, therefore it's not going to cancel. Typically you'll always look for things like things getting cancelled, but that's not going to happen here. And of course you now have a mixture of things like P infinity over rho naught and P naught over times 1 over rho infinity times, again you have a P naught over rho naught term. So this is beginning to look like if you're now looking at like an xy plane, you're now beginning to look at a curve that's kind of like some axy plus bx plus cy plus d equal to 0, right. So if you now have like a leading order term like xy, right, what would that actually signify? If xy equal to 1, if that's what you had, okay, that is like a is equal to 1 and d is equal to minus 1, then you would simply, and b and c are 0 in whatever format that I just template that I just explained. You would be looking at a rectangular hyperbola, but since you also have a P infinity divided by rho naught term and a P naught divided by rho infinity term, we also have some b's and c's that are non-zero. Therefore it's not exactly a rectangular hyperbola, but it's going to be modified, so it is going to be like a hyperbola here. So hyperbola is going to now look like if you now had something like that. Okay. Now we don't know exactly if it's going to be a rectangular hyperbola in this P infinity 1 over rho infinity domain. It's very likely that you could have this cross over to lower value. Okay, so I'm not saying that this exactly is the curve at the moment, but what we are trying to do is to sort of construct this curve as we go along. Okay, well, why did we want this curve? Because we wanted to solve these conservation equations across this continuity to locate product properties given the reactant properties, including u naught, which is something that we are not very sure that we know to begin with, and u naught is actually embedded in the slope of the Rayleigh line. But the Hugoniot, so this is what's now called so this rectangular hyperbola is what is called as a Hugoniot curve, right, and the Hugoniot does not involve any m dot. In other words, it is like a purely thermodynamic curve. Okay, so the flow information is actually buried in the Rayleigh line, which is a mixture, which is a combination of continuity and momentum together. So that carries the flow information, whereas the thermal energy equation effectively is not carrying any flow information there. And then what we are looking for is a intersection of these two these two curves, that is the Rayleigh line and the Hugoniot curve, and sure enough we find that there are a couple of intersection points, which will now tell us that if you now started out with the P naught and 1 over rho naught as the reactant conditions, and this particular point is typically referred to as what is called as the origin of the Hugoniot plot. Right. And then what we want to see is where is actually the conservation equations, where are they satisfied again, right. So what you will find is that you now get like about 2 points where they could be satisfied. So you have like at least 2 possible solutions. This is a great progress that we have done, starting from when we didn't have any equations to solve. We had like an entire plane to search the solution, and then when we now had the Rayleigh line, we now reduce the possible set of points to a line rather than a plane. And since you now also have the energy equation in the form of the Hugoniot curve, we look for a point of intersection. Of course we are now beginning to see like about 2 points of intersection instead of just 1, right. So we now have to look at what are the different possibilities for these 2 points of intersection. Will it be only 2, or will it be, when will it be 1, and if it is 2, what are the possible 2 values, and so on, right. Obviously this is a curve which has the same sign for the curvature. That means it is always like concave facing upwards and upwards to the right. Therefore since the curvature does not change sign, you do not have any points of inflection in the Hugoniot curve. When a straight line intersects with this, you can have up to 2 intersection points. You are not going to expect more than that, right. But you could look for 1 intersection point or none. When would you get 1 intersection point? If the Rayleigh line were tangent to the Hugoniot, right, or the Rayleigh line never really intersects with the Hugoniot, then you do not have any solutions, right. So there is some hope. We are now looking at 0 solutions, 1 solution, or 2 solutions, not more than that. Good. So with this picture, we now see how to go about constructing this plot a little bit more carefully, right. The first thing that we notice is if your Q is greater than 0, okay. So for Q greater than 0, the Hugoniot curve passes to the right and above the origin, that is there, okay. For Q equal to 0, you could also check this if you want by plugging in values for P infinity and rho infinity. For Q equal to 0, the Hugoniot curve would pass through the origin, okay. So right. Now what is Q? Q is essentially negative of what is called as H infinity naught minus H naught naught, and H infinity naught and H naught naught are in turn sigma I equals 1 to n delta HFI yi naught delta HFI naught, and sigma I equals 1 to n yi infinity delta HFI naught, right. So it's only because of the compositions at at the naught condition and the infinity condition, the delta HFI naught is the same for both because it's a standard heat of formation, right. So we are now getting these different HI naught and HI infinity, and then the difference between the two is essentially the chemical heat release with a negative sign, okay. So that's a chemical heat release. If Q is equal to 0, that means you are not having any chemical heat release. So if a chemical heat release is not there, essentially we are talking about a non-reacting mixture, right. If you have a non-reacting mixture with a Hugoniot curve, that is somewhat similar to what you might have gone through in a basic gas dynamics course, where you are still looking at, as a matter of fact, if you now think about how we had this equation, we had like a H naught plus half U naught squared is equal to H infinity half U infinity squared, that's without the Q, right. And that's exactly the same as what you would call as an adiabatic energy equation that you would write for a energy conservation across a shock, okay. So across a shock you would find that the stagnation temperature remains the same, the stagnation enthalpy particularly remains the same, right. That is true when you don't have any heat release, okay, or any chemical heat release. So a curve that actually passes through the origin with Q equal to 0 is what is called as the shock Hugoniot, right. Now that tells us that if you now have a Q not equal to 0, and we expect typically the Q to be greater than 0 rather than less than 0, we are not looking at cooling kind of thing, right. So what is it when you now have a wave that is reacting in addition to being a shock, right. So you are now beginning to think, and then of course a shock is actually either phasing a supersonic flow or it's traveling at supersonic flows, this is supersonic speeds relative to like still reactants. What is it? I mean, this is not something that we thought about. We started talking about something like low Mach number conditions and all those things, but now we are getting into something. But of course in what we are doing now, we are not really making the low Mach number assumption, right. We should be now game for any kind of Mach numbers that are approaching your wave, but the language that we are beginning to use is now beginning to admit the possibility of supersonic flows, right. Okay, when would that happen? So let's just do this a little bit more carefully. Let me declutter this picture of all the terminology that we are now used to, and we just want to now redraw this only with things that we want to now take so let's say you now have the origin. Again, I'm not going to name it now, and let me first draw the Hugoniot line a little bit farther away, and let's now say that you go here and here, and let's see what happens here. Your Rayleigh line can have only a negative slope, right. So if this is your origin of the Hugoniot, the Rayleigh line can fill only the third quadrant, sorry, the second quadrant or the fourth quadrant, right. It can't go like this, so it can't get into the first quadrant, it can't get into the third quadrant. So this part of the Hugoniot is never going to be used, right. So we now have to erase this part away from consideration. We just don't want to worry about that part of the Hugoniot at all. We will worry about a part of the Hugoniot that starts from where 1 over rho infinity is equal to 1 over rho naught, okay, another part of the Hugoniot where P infinity is equal to P naught. What does that mean? If you were to now have a solution that is somewhere here, that means your Rayleigh line is sort of passing like this. It means two things. One, your final pressure is about the same as the initial pressure. Okay, the pressure hardly changed when the flow went past this wave. Second, this Rayleigh line has almost like a zero slope. That means the wave isn't moving much. So it's possible that if you are talking about nothing, okay, so it's like you don't have a wave, so obviously the pressure didn't increase. Yeah, that can't be true because the density increased. Well, the density decreased. So there was a density decrease that was primarily because if the pressure remains the same and the density decreased, that's because the temperature should increase. So you had a heat addition, all right, that is the reason why the Hugoniot is shifted away from the origin in the first place. So you had a heat addition, correspondingly you had a temperature rise, but you didn't really have a wave that was moving fast enough, and you didn't have a corresponding pressure rise. This is now beginning to look like what we were talking about for what's called as low Mach number conditions, right. The pressure is approximately a constant, right. So low Mach number simply means that the wave isn't moving too fast, or relative to the wave the reactants aren't moving in too fast, right. Therefore the Mach number is very low. So you now have one branch of the Hugoniot that is now beginning to correspond to waves that are moving kind of very slowly, okay, and the fastest wave could possibly have a slope that is tangent to this at this point. That's the fastest wave that is possible. That is the highest m dot that this branch of your Hugoniot will intersect. Okay, if you for any faster waves, the Rayleigh line is now going to actually go downward and fail to intersect this branch of the Hugoniot. Will that intersect the other branch? Not immediately. You now see that you have to actually go to a still steeper Rayleigh line that will begin to intersect the other side. Or if you are thinking about an experiment where you want to conduct a stabilization of a wave by sending in reactants at faster and faster flow rates, right. Between this particular flow rate and that particular flow rate, you just can't stabilize a flame at all. And then you again begin to stabilize flames for all Rayleigh lines that are now having steeper slopes than this. You can have points of intersection until you get to this point which has an infinite slope, right. It is kind of, again, just like how a zero slope is almost impossible and we are thinking about like very low velocities, right. Infinite slope again is not something that we want to think about, but very high, essentially very high slopes, that means very high velocities for which the pressure jumps but the volume didn't change a lot. So this is more like a isochoric process. That's what you started out with was an isobaric process, right. So in the one extreme you started out with an isobaric process corresponding to very slow waves, right, and then you could think about a little bit faster waves but with a certain decrease in pressure, not a whole lot of decrease, okay, but from here to here you see that the pressure is decreasing only a little bit, okay, but the expansion, that is the density decrease as you go this way, 1 over density increases, so density actually decreases. There is a significant amount of expansion that's going on right from the beginning because of the heat addition, and then nothing until you get to very fast waves, and you can now get these very fast waves to go all the way to the other limit where you are getting close to an isochoric process, that is like a constant volume situation, right. And there again, because of the heat addition, you hardly have any change in volume, but essentially the pressure increased, right. So what you then have is, this is what is called the lower branch of the Hugoniot, and this is what is called as the upper branch. Right. And we want to call these points the tangents, the tangent relays intersecting at these points as the LCJ point, and this is the UCJ point. CJ stands for Chapman-Jouguet right. So the LCJ indicates the highest velocity of what's called as deflagration waves. So this is the lower branch corresponds to what is now called deflagration, right. So LCJ is the fastest deflagration wave, and the upper branch of the Hugoniot corresponds to what is called as detonation, and UCJ corresponds to the slowest detonation wave. Right, and the m dot UCJ is still significantly greater than m dot LCJ. That means the slowest detonation wave is still much faster than the fastest deflagration wave. That simply means that you now have two classes of waves that are significantly apart. There is really no overlap at all in their wave speeds, and in fact what I should actually say is this should be much greater than. So in terms of wave speeds, like instead of writing m dots, if I were to write u naughts, assuming like they started out with the same rho naught, right, what this now, see I told you that I don't know what the u naught is, right. I am still not going to know the u naught until the end of this exercise, but I am beginning to get some ideas about what the bounds of my u naughts should be for two different kinds of processes that we are now beginning to think about, namely deflagration and detonation, right. So what we are talking about here is for detonation, for deflagration waves, your u naughts of the order of a few tens of centimeters per second under laminar conditions, but your detonation waves, so to a few tens of centimeters per second is still less than a meter per second, but your detonation waves are typically of the order of a few kilometers per second. So you now see that there is like about 3 to 4 orders magnitude difference, a factor of 3 to 4 orders magnitude difference between the detonation velocities and deflagration velocities, right. What we should further notice then is that we want to think about the deflagrations going as subsonic waves, whereas the detonations are going at supersonic waves. but before we do that we want to now quickly go through some mathematical properties because we started out with mathematical equations for these like this one, and then we noticed that goes like a hyperbola, and then we of course had a simpler mathematical expression representing a straight line, very easy to see this for the Rayleigh line, and we are now looking at these intersections and so on. What I would like to first of all before we proceed further is to give you expressions, and these are not very difficult for you to derive, and these are all like typical exam exercises, okay. So you can figure out, for example, depending upon the Q, what is this point, okay, the lowest value of 1 over rho infinity possible for the detonation branch, and where is this point, for example, what are the coordinates of your LCJ point, that will also depend on Q, and what are the maximum, so what's the maximum value of 1 over rho infinity that is possible, right, and what are the maximum values of P naught that is possible, that is of course equal to P infinity, and what's the minimum value of P infinity that is possible. What you will find is you will notice if you now try to actually look at the mathematics of this would ultimately go and intersect the x axis or the abscissa, right, and where it intersects is where you would get the maximum value of 1 over rho infinity, and the corresponding value of P infinity would be 0, okay. As a matter of fact, what you will find is this rectangular hyperbola asymptotes to a value of P infinity that is negative. So what you can actually do is to go ahead and find out the horizontal asymptote for this rectangular hyperbola, and you should find that that's negative, and since you can't admit negative pressures in reality, you don't worry about where exactly it asymptotes, and you have to stop thinking about it at where it hits the abscissa, that's corresponding to your P infinity equal to 0, and then there is like a corresponding 1 over rho infinity, that's the maximum value to which the products can expand, right. Similarly, you can look at the upper branch and find out that the lowest value of P infinity it can take will depend on Q, but the corresponding 1 over rho infinity will be equal to 1 over rho naught, right. Then you can also locate this point, the UCJ, and then where does it go? So what you will have to find out is there is a vertical asymptote which is having a positive value of 1 over rho infinity, that is the lowest 1 over rho infinity that it can take, but it is now going to asymptote to that means the maximum value of P infinity that it can take is infinity when it hits asymptote eventually at infinity, right. So these now give you limits for these pressures and densities that it can take in these different branches of the Hugoniot curve. So we can go through that, but I think even before that we can point out that so in the deflagration branch, P infinity is less than or equal to P naught, right, and 1 over rho infinity is greater than, it's certainly greater, it's not greater than equal to, because it would be greater than or equal, it would be equal to 1 over rho naught only for Q equal to 0. For positive values of Q you can never get your 1 over rho infinity to be equal to 1 over rho naught, so it is always greater than 1 over rho naught for Q greater than 0, that is rho infinity is less than rho naught. The density decreases and the pressure decreases, okay. For Q greater than 0 you always have T infinity greater than T naught, this is heat addition, so the temperature increases, right. So with the temperature increasing, density decreasing is not news, but pressure decreasing is indicating these two together, then given this means you now have the products go through an expansion, right. So it's when you have an expansion is when your pressure decreases and your density decreases even with the temperature increase, right. So a deflagration branch corresponds to an expansion wave, right. On the other hand, if you now look at the detonation wave, in the detonation branch, your P infinity can never be equal to P naught for Q greater than 0, right. Only for Q equal to 0 will the Hugoniot pass through the origin, and you have only one tangent relay, right. But for Q greater than 0, P infinity is always greater than P naught for Q greater than 0, which implies again T infinity is greater than T naught. You always have a heat addition that you're having in mind in both cases, right. T infinity is greater than T naught, all right. So P infinity is always greater than P naught, and 1 over rho infinity can be less than or equal to 1 over rho naught, right. So the highest value of 1 over rho infinity that you can hope for is this, right, that is equal to 1 over rho naught. All other 1 over rho infinities are going to be less than that, and this implies that is rho infinity can be greater than or equal to rho naught. That means you now have a density increase corresponding to a pressure increase accompanying a temperature increase. When the temperature increases, you would like to think that the density should actually decrease, but if the density increased accompanying a temperature increase, that simply means that the pressure increased a lot more, right. Sure enough, you look at the way the curve goes, it's going crazily along the pressure axis, right. So the pressure is obviously increasing a lot. So taken together, all these things mean that we now have a compression wave, right. So a detonation basically corresponds to a compression wave. So we talked about a shock Hugoniot. We are now beginning to look at one of the branches actually corresponding to compression. So it's all kind of going together. You can see that there are elements of what we have done before in gas dynamics beginning to look like a special case of what we're talking about, right. It's a special case in two ways. One, first of all, it's a non-reactive case. Okay, what we went through in gas dynamics is basically a non-reactive case as opposed to a reactive case here, and the moment you have reactions, then it belongs to only one part, which is like the supersonic propagation, as we will see and show, corresponding to detonation, whereas there is also another part which is corresponding to deflagration, that is subsonic propagation, and where expansion happens rather than compression. Alright, let me also say one more thing. So now that we have also acclimatized ourselves with some more here, we could further actually divide this into 5 parts, I should say 4 parts rather. So you now have, you can now divide your upper branch as something that's above the UCJ, and something that is below the UCJ. You can divide the lower branch as something that is to the left of LCJ and something to the right of LCJ. So let us now call this region 1, this is region 2, this is region 3, and this is region 4. So we essentially are looking at the upper branch as a detonation branch, the lower branch is the deflagration branch. So what we would like to call this as region 1, at the moment they are just names, we just don't still understand them more completely, but let us just give the names first and then start understanding, because that will kind of aid us in understanding. So region 1 is essentially what is called a strong detonation, and then of course you now have CJ detonation, and then we have region 2 that corresponds to a weak detonation, and then we have region 3 this corresponds to a weak deflagration, and then you have the CJ deflagration, and then we have region 4 that should by now be easier for you to figure, that should be called strong deflagration. For you to remember this at this stage, let us just say that when you are now looking at a region that is above the CJ point here, the UCJ point here, what that simply means is we are now looking at a solution. So that means your Rayleigh line has to actually pass somewhere there, and then you are looking for a intersection somewhere there, right. That means the Rayleigh line is obviously steeper than the tangent Rayleigh there, that means the wave is propagating faster there, right, and it is now leading to a very high pressure and a very high density, that is a low 1 over rho infinity and a high P infinity. Say a very low 1 over rho infinity means a very high rho infinity. So this is actually corresponding to a lot of pressurization and a lot of compression. So that is why we are basically saying strong, but it is going to be a little bit more than that. We will have to see what is the propagating Mach number for the wave and what is the downstream Mach number for the products. It's based on that actually we now give this nomenclature that this is strong detonation, but at the moment you can clearly see that this is pretty strong in the sense it is having a lot of compression, whereas a weak detonation is just as fast. If you were to now look at a solution that is here, its Rayleigh line is pretty steep as well, just as steep as well, so it's pretty fast alright, but it is not leading to a very high pressure, and the departure from the origin is not a lot in the 1 over rho infinity axis. So your 1 over rho infinity is not a lot lower, therefore the rho infinity is not a lot higher, therefore you are having a smaller amount of compression when compared to the strong detonation. So relatively speaking we would like to think of this as a weak detonation. Okay, what we will actually find is when you now have a flow that is going through a detonation wave, just like in a normal shock, you should expect that if the flow is approaching the wave at supersonic speeds, if the shock is very strong, you should expect the flow to actually become subsonic all the way. That's a mark of its extent of compression. So if it has been compressed a lot, the flow also gets decelerated, right. So a lot of compression would mean a lot of deceleration all the way down to subsonic levels, whereas in a weak detonation you expect that the downstream product flow is still remaining supersonic, although not as supersonic as the upstream reactants. There is the deceleration alright, but not down to subsonic levels. Correspondingly, the CJ detonation should mean that of course you are going through a supersonic reactant flow reaching up to the wave, but the products correspond exactly to sonic conditions. That's what is denoting a CJ detonation. Similarly, if you now begin to look at this side, what it means is in a deflagration we are looking for an expansion. So when you're now looking for an expansion, that means the pressure should decrease and the density should also decrease. If you now look at this region, the pressure decreases not a lot and the density decrease or should say 1 over rho infinity increase is also modest. Therefore a rho infinity decrease is also modest, right. So you are now not having a fairly large decrease in P infinity and rho infinity, and therefore you are expecting like a weak deflagration. Okay. So you are now looking at a Rayleigh line that is corresponding to a velocity that is still lower than the CJ deflagration, right, it is slower, and so correspondingly you are not really expecting a large decrease in pressure and density. Okay. But for this low deflagration you still can intersect over there. So this wave is just as slow, but it is actually causing a large decrease in pressure and a correspondingly large decrease in density, right. That is a lot of expansion that is going on, and that is why we want to term it as a strong deflagration, right. So when you now have a large expansion that is going on, proportionately you are now expecting the flow to accelerate. So when a reactant flow is actually going through a deflagration wave, it tends to accelerate, and this is actually common practice. So in all these things we always try to relate to what we already have experience with. So what I would like to suggest is when you are dealing with detonation waves, you now recall what happens in gas dynamics, what you have learnt in your one dimensional gas dynamics from your undergraduate, let us say if you have gone through a gas dynamics course in your undergraduate level, you can recollect what happens across a shock and try to modify your thoughts to accommodate reactions and so on. When you are thinking about deflagration waves, this is actually more commonplace in terms of daily experience, like what happens in like in a Bunsen burner for example, right. So if you now have a Bunsen burner and then you have like a cold reactant flow that is approaching the Bunsen burner, and then it goes through the flame, and the flame is like a conical flame, and the flow goes through this, it now expands and then kind of goes like that. Okay. And then you can also see that occasionally, and this is not very difficult for you to think about as a thought experiment, or even go back and see if you can do this and see for yourself. When you now have like an inclined flame like this in a Bunsen burner, and if you had like a little particle that is kind of glowing, okay. So if you now see how this glow happens as it goes along, when it passes through the flame it goes much faster when compared to when it tried to approach. So it is like a little spark of some particle that is just glowing. You can clearly see that it just goes faster, right. So when you now have a deflagration wave, the flow accelerates when it goes past it because it is expanding, right. Now while you are here you are not expanding a whole lot, and that is because it is a weak deflagration, and therefore you started out with the flow approaching you at subsonic speeds and you are accelerating to further faster but still subsonic product speeds. That is the mark of weak deflagration. But when you now go past the LCJ over here to the strong deflagration, what that means is you are now having a very large amount of expansion that is going on, correspondingly there must be a very significant amount of acceleration that goes on, to the extent that we end up finding that the products actually have supersonic speeds by the time they are getting past this wave, although they started out with subsonic conditions for the reactants. Correspondingly, just like how we found in the case of UCJ, what this means for the LCJ is the approach velocities for the reactants is subsonic, alright, but the flow accelerates through the wave to exactly sonic conditions beyond for the LCJ. Now if you really think about it, this is getting a little bit more fascinating, or it's unbelievable, fantastic. Okay, how can I have a wave that started out to be subsonic go through a flame and accelerate so much as to become supersonic? Is it possible for me to do so? The answer is we don't come across that at all, right? So in Bunsen burners and stuff you don't really get supersonic flows. So what's going on? The answer there is outside the picture of what we are talking about. We started out with the mass conservation equation, we started out and then we went through the momentum conservation, and then we went through the energy conservation. We also talked about the species conservation, but the energy conservation, keep in mind, is essentially coming out of the first law of thermodynamics, but we never really considered the second law, okay, and we will never do that actually, except to state that this part of the wave, that is the strong deflagration, is not possible if you now start taking second law into account, and that's the reason why you will never really find a wave starting from subsonic flows going through a strong deflagration to accelerate all the way to supersonic speeds. That typically doesn't happen because it violates second law, right? And I think I may be able to show that briefly later on, but let me also point out that I will try to show, first of all, that detonation waves, all detonation waves, or in fact I should say all detonation waves travel at supersonic speeds, and I should also show that all deflagration waves travel at subsonic speeds. The way I would like to I would show this is to consider the CJ detonation and the CJ deflagration. I would like to show that the CJ deflagration is supersonic, which means the slowest detonation is supersonic. That means all of the detonations are going to be supersonic, and I am going to show you that the fastest deflagration, the lower CJ deflagration, is going to be subsonic, therefore all other deflagrations are subsonic, right? And then we will also consider the downstream Mach numbers for the UCJ and the LCJ and show that they are actually 1, thereby we can clearly see how these things are demarcated, right? But before we do that, let's go back and just write out the properties of the Hugoniot curve on where they intersect, what the asymptotes are, and all those things in the next class. Thank you.